Hello, welcome back to another episode of Chemistry. Today, we're just going to talk about Le Chat, changes to equilibrium. Specifically, I'm going to go through those concentration time graphs to help you unpack that a little bit. Now, concentration time graphs. Have a look at this graph. Have a look at the reaction. Now, what we have to do here is we have to identify the change that we make at T. So T here. You've got the balanced equation for this equilibrium reaction. You've been told that that's positive, which means what? That's endothermic. Up until point T, we're nice and steady in terms of the concentration. So you know that at this point here, you're at equilibrium. And why are you at equilibrium? Is because the concentrations aren't changing for anything, which means the rate of you making stuff and the rate of you breaking it down is actually exactly the same. Then all of a sudden, at this point here, something happens. And it only happens to one species in this whole reaction, and that is to NO. Oh, and you just have to think to yourself, what could possibly happen? What could I have done to make the concentration of NO almost instantaneously increase? But only that and nothing else. And the only reason that we have for that is we actually add NO, right? So the change that was made at T was we added, cool. Now, again, same reaction, but now what we have to do is we have to describe the impact of that change at time T. So we know that the change at time T was that we added NO. Now, we can look at the graph and see the shape and the changes, and or we can start with looking at the equation and then see what would happen in that instance. So, for example, you can see that when you add NO, in order to partially oppose that change according to Le Chat, what will happen is you'll start to use NO, which makes absolute sense. As a result of that, you also decrease the concentration of Cl2. So that tells me that I'm also using Cl2 in the process in order to make NOCl. So that's one way to look at it, and you can describe it like that. However, you're not really understanding what's happening and why that's happening. So if we have a look here, let's do an overall little table to help us identify what's going to happen and then attribute that back to the reaction. So what the change was that you increase NO, right? You added NO. Now what you want to happen, so let's call it the goal. The goal then is to decrease the amount of NO. How will you do that? You want to use the NO. Cool? And that's irrespective of what the reaction is currently looking like. We know that the aim of the game and how, according to Le Chat, this system is going to respond is it's going to use the NO. Then you go and you look at the reaction, you go, cool, NO is a product if we go from left to right. So to use the NO, what we have to do is we actually have to favor the backwards reaction. In order to do that, what's going to happen is we're going to decrease the NO, but in the process, we also have to use the chlorine gas in order to produce the NOCl. You can see that reflected on the graph. Now that graph makes a lot more sense. Because we're adding NO, the system's going to want to partially oppose that change by decreasing the NO, as we can see here. In order for that reaction to happen, you know that you have to use NO in favor of the backwards reaction. Chlorine also has to be used in the process, as you can see here as well. As a result, I'm making NOCl, as you can see here. So what we say is, cool, at time T, you can see that NO was added. Now, according to Le Chat, the system will partially oppose that change by decreasing the amount of NO by using it. This means that you're going to have a backwards reaction being favored. Or you can say that equilibrium shifts to the left a little bit in terms of going backwards like that. What that means is you're going to use the NO and you're going to use the Cl2. You'll see the concentration of both of those decrease. As a result, making NOCl, you can see that concentration increasing, as you can see here in the graph. Now, what I want you to really notice is the partially opposed change. How that's reflected in a graph is this, and you have to pay attention to this, especially when you're going to draw your own graph. See how, yes, we're decreasing the amount of NO, but compared to when equilibrium was first reached, which is about down here, that concentration doesn't reach where it was before. That's the partially opposed change part. So if you ever look at this graph, or if you ever have to draw the graph, when you make that change, you have to make sure you don't reach the concentration of the original equilibrium before the change. That's the partially opposed change part. And that's when teachers and examiners can tell that you don't understand Le Chat. So many students miss out on this part, and I want to show you so you can't unsee it, so you don't make the same mistake. When you're looking at these graphs, especially again when you're drawing these graphs, you have to understand that the change is reflected in the mole ratio. So here, have a look at the amount of change that you see here in NO. Then compare it to the amount of change that you see in Cl. According to the balanced equation, there's a 2-to-1 ratio, right? So for every 2 moles, for example, that you use, you will only use 1 mole of Cl2. So you can see here that the change in the Cl2 is half as much as NO. Then you look and compare the change with the NOCl. You can see that the ratio between NO and NOCl is a 2 to 2, which means that the size of the change for both of those species should be the same. So you can see here, the extent of the change of NO and NOCl is the same. Whereas for NO compared to Cl2 only changes in terms of concentration half of the change because of the 2 to 1 ratio. Please don't forget that. So when you're looking at these graphs, there are things to look out for, and that is, what is the shape of the change? Is it going to be gradual, or is it a spike or a sharp spike like what we saw in the example? What species is it applied to? Is it only one, which is what we saw here for NO, or is it to all of them? If it's to all of them, you have to think about what change has to happen that impacts everything. So that might be volume. When you're changing volume, you're impacting the concentrations of everything and the pressure of everything. If you're changing the temperature, it's a gradual change, but it affects everything. If you're adding or removing, you know that the concentration is only affecting one species. So, for example, you see how this is affecting everything all at once? That's because there's a change that's applied to the whole system. Here, the volume is decreased, and when the volume is decreased, there's going to be an increase in concentration. So you can see that here. It affects the whole thing. As you can see here, also, this here is affecting everything, but it's a gradual change. Now, the chances are that when this happens, when you see a shape that's gradual to all, that's probably going to be a temperature. So these are really cool things to look out for to help you understand what changes have been made. So let's summarize. For these concentration time graphs, have a look at the change and the nature of the change. Is it one thing? Is it everything? Then use Le Chat to explain the impact of that change. So if an increase in concentration, what does Le Chat say you're going to do? And then pay attention to the magnitude of the change because that should be reflected in the balanced equation. Thank you so much. Hope that was helpful. Always remember, no matter what anybody says, yeah, you can.